Hello all. Our next chapter is distributed mutual exclusion algorithm, and this chapter we are referring from book that is Advanced Operating System by Mukesh Singhal. So let's start. Now whenever we hear this term mutual exclusion, it means we are working with a type of resource called shared resource. So there are two types of resource, one is shared, the other one is non-shared. If it is non-shared, that means the computer system or the node is not sharing that resource with any other computer system or the node. Now, if it is a shared resource, that means that resource is available to be used by any other computer system or node or processor in the distributed system. So this was one of the major advantages of distributed system, wherein a resource can be shared to other node or the computer system. Now the shared resource is also of two types. In the first type, the resource is available to be used by multiple processors simultaneously. So that means any number of processors can use that resource at any point in time. Okay, so that means at some point in time, if there are n number of processors who want to use that resource simultaneously, then the resource is available or allowed to be used. Now in another type of shared resource, though the resource is available to be used by any processor in the distributed system, but there is a condition, and the condition is at any point in time only one processor will be allowed to use. So they will have to wait, the other processors will have to wait. So that type of resource is called mutually exclusive resource, or it is also called as critical section. So I hope you all have heard about critical section in operating system subject. The same concept is there in distributed system also. So critical section is nothing but a shared resource, but the condition is only one processor will be allowed to use that critical section or that shared resource at one point in time. Now in distributed system there will be so many processors and so many shared resource or so many critical sections. Now this particular chapter focuses on figuring out at any point in time which processor who is currently requesting for, there can be so many processor who might be requesting to use the critical section simultaneously. Okay, now what is this mutual exclusion algorithm is? This mutual exclusion algorithm, they will be dealing about solving the problem of determining which processor is allowed to use critical section at any point in time. Okay, so now that means in this particular chapter we are mainly referring for only this type of resource, that is critical section, a resource which is allowed to be used by only one processor at a time. And what is this mutual exclusion algorithm is? It is the algorithm that deals with identifying the processor that is allowed to use critical section at any point in time. So whenever critical section becomes free, a mutual exclusion algorithm will be executed in the distributed system, and that will take out one of the requesting processor. Okay, that will identify one of the requesting processor, and the critical section will be given to that particular selected requesting processor to use. So this is about the mutual exclusion algorithm. Now there are various types of mutual exclusion algorithm. In the distributed system, which is broadly classified into two categories. One is called token based algorithm, the other one is called non token based algorithm. So in token based algorithm, the processor, okay, in the distributed system there will be one token that will be present. Okay, for each critical section one token will be generated. Now only though that particular processor will be allowed to use critical section which has got the hold of the token. So there are various types of token based algorithm. Okay, and all token based algorithm work with the same fundamental concept, and the concept is a processor is allowed to use critical section only if it has received or it has got the hold of the token. So for one critical section there will be one token, and any processor who wants to use that critical section will have to get that particular token. Now, as I said, there are various types of token based algorithm, and how different algorithm differs is based on the way they do the searching for the token. Because in distributed system there are so many, there will be n number of processors, and which processor is currently having the token, or there are n number of processors fighting to get the token. Now which particular processor should be given the token next? All the decisions are taken based on the type of algorithm, type of token based algorithm that we will be using in the distributed system. So token based algorithm means a processor will have to get the token, and then only the processor will be allowed to use the critical section. Now another category of mutual exclusion algorithm is non-token based algorithm. So in non-token based algorithm there will not be any token. Now how the processor will be identified to use, next processor will be identified to use the critical section is based on some consensus. Okay, so there will be some set of rules that will be set by the type of non-token based algorithm that we are using, and whichever processor at any point in time satisfies those set of rules, that particular processor will be allowed to use the critical section. Now those set of rules or the consensus will be made based on, will be made in such a way that at any point in time only one processor will be satisfying all the criteria that the algorithm has set. So the criteria will be defined in such manner. So what happens in non-token based algorithm is, in the non-token based algorithm all the processor they will be fighting to satisfy the set of rules, and at any point in time whichever processor satisfies that set of rules, that particular processor will be allowed to use the critical section. And remember that the algorithm will be designed in such a way that only one processor will be satisfying all the set of rules that the particular algorithm has defined. So in this chapter we are going to see various types of algorithms. Some of them are token based algorithm and some of them are non-token based algorithms. Now the next topic is requirement of mutual exclusion algorithm. So presently there are various mutual exclusion algorithm. So n number of mutual exclusion algorithm exist, but which mutual exclusion algorithm is required, or I mean to say that what is expected from any of the mutual exclusion algorithms, this is what we are going to see next. So it is not necessary that all the requirement has to be satisfied by all the mutual exclusion algorithm, but as a user of distributed system, from any mutual exclusion algorithm they expect the algorithm to satisfy these requirements. Now the first requirement is mutual exclusion algorithm is expected to be free from deadlock. So deadlock means there should never be a situation wherein different processors are requesting for a critical section but they are not getting because they are in the deadlock condition. That is, for example, let us say there is one critical resource R1, another critical resource R2, and let us say there is processor P1 and P2. Okay, now what is happening is P1 is requesting for R1, R1 is already allotted to P2. Now P2 is requesting for R2, but R2 is already allotted to P1. Now this is a deadlock situation. A cycle has formed wherein the problem here is P1 and P2. P1 to finish the execution it needs R1, P2 to finish the execution it needs R2, and both of the resources are not free, okay, which cannot be given to any other processor. Now a deadlock situation is a situation wherein none of the processor will be able to proceed further, okay, because the condition, they are into that condition wherein they neither complete their execution, okay, nor they are getting the resource which they need to finish their execution. So this kind of situation should not be should not happen by using a mutual exclusion algorithm. Next requirement of mutual exclusion algorithm is freedom from starvation. Starvation means a processor which is requesting for a critical section but is waiting indefinitely. That means the processor is waiting for a very long period of time to get that critical section, wherein in between the other processor is repeatedly getting the critical section. So that is called starvation condition. Okay, so starvation means, let us say there is a processor P1 who wants to use a critical resource or a critical section. Now it has sent a request to use the critical section, but that processor is not getting that critical section, wherein there are some other processor which is repeatedly getting that critical section more than once. So this kind of condition is called starvation, and what is expected from mutual exclusion algorithm is this starvation should not happen while using that algorithm for satisfying the mutual exclusion property in the distributed system. Next is fairness. Fairness requirement says that the order in which the request was made for the critical section, or if we see from the other end, from the critical section end, that means the order in which the request was arrived, okay, to the system which is currently managing the critical section, in that order only let us give the permission to use the critical section. So that is fairness. So in which order the request was made, or in which order the request was arrived to the critical section, in that order only it is expected that the mutual exclusion algorithm will be providing the resources. Though all the mutual exclusion algorithm may not be fair, but these are only the requirements or the expectations. Now the last one is fault tolerance. Fault tolerance is one of the important characteristics of distributed system, which is again applicable for mutual exclusion algorithm. So it is expected that the mutual exclusion algorithm is fault tolerant. That means if something happens, okay, like there can be many reasons because of which, let us say, a critical section could not be given to one of the processor. Okay, if that kind of fault happens in the distributed system, that should not affect the functioning of entire distributed system. That means that should not affect the critical section allotment to the other processors. So other processor, they should be able to get that resource, okay, even if some fault has occurred in the distributed system. So that is your fault tolerance. Now next is performance of mutual exclusion algorithm. So as I said, there are many if you search in internet also, you will find many mutual exclusion algorithms. Now how you are going to decide that which mutual exclusion algorithm is better is by comparing their performance parameters. So the performance parameters of mutual exclusion algorithm usually are 4. The first one is number of messages necessary per CS execution. Second one is synchronization delay. Third one is response time, and the last one is system throughput. So these are the parameter or the metric based on which we will be able to identify that which mutual exclusion is better than the other mutual exclusion algorithms. Now the first metric is number of messages per CS invocation. Now this is about, for any processor to use the critical section, how many messages message communication that processor has to do. Okay, in the simplest one, the processor will be sending a request message to the critical section. Then whichever system is managing or controlling this mutual exclusion portion, they will be sending the permission message, which is again a message. Then finally the processor will be using the critical section, and after using, the processor will be sending a release message to the system admin. Okay, so that way, now to use critical section for one time, how many messages has to be communicated by that processor? That is called number of messages per CS invocation. Now the objective will be to reduce this number of messages per CS invocation. So whichever algorithms number of messages per CS invocation is less, that algorithm will be considered better based on this performance metric. Next performance metric is response time. Response time means it is a time interval or request wait for its CS execution to be over after its request message has been sent out. So what happens is that whenever a process wants to use the critical section, that process will not be allowed to directly go and use the critical section. Obviously, if some other processor is already using, then that is going to affect the integrity of critical section. So that is not allowed. So whenever a processor wants to use the critical section, the processor will have to send a request message. Okay. Now after sending request message, for how long that processor will have to wait? Okay, on an average, after the request message is sent out and up to the execution of the critical section. So response time is total time duration starting from the message sent to the request message sent in the distributed system till the point when that processor gets the critical section and finishes the execution of critical section. So that is called response time. Okay. So let us say this is the timeline. Let us say that at this point the processor decided that it wants to use the critical section. Now this is the time when, let us say, the processor sent the request message out in the distributed system. Now where that message will go, okay, that depends on the algorithm that we are using. Now after some time, let us say that processor got the permission to use the critical section, and let us say this is the point when the processor is allowed to enter the critical section. So once the processor enters the critical section, the processor will be executing it. So it will be based on the execution time of the critical section, and after execution, let us say this is the point when the processor is coming out of the critical section. So this entire duration or the entire timeline is called response time. Okay, which includes the execution time of the critical section. Let us say RT is the response time and E is the execution time. Now the next performance metric is system throughput. So system throughput means distributed system, in the distributed system, by using that particular mutual exclusion algorithm, in 1 unit of time, how many requests was satisfied. Okay, so that means for one critical section there can be n number of resources that I have discussed previously. Now for taking 1 unit of time, how many processors request was satisfied, that is called throughput. Now there is a formula for throughput which says that system throughput is equal to 1 divided by synchronization delay plus E. Okay, so we forgot to discuss about synchronization delay, right? So synchronization delay is the time after the site leaves the critical section and another site enters the critical section. So let us say that this is our critical section. Okay, so site here is nothing but the processor. So let us say at this point in time, so one processor, let us say S1, is allowed to enter in the critical section. Now S1 will take E amount of time to execute in the critical section, and after that S1 will be coming out of the critical section. Now S1 has come out of the critical section. After how long another site is entering in the critical section? So it may not be immediate, because in between mutual exclusion algorithm will have to take a decision regarding which another site will be allowed to enter in the critical section. So what is that duration, wherein the mutual exclusion algorithm will be taking this decision and informing that particular processor to enter in the critical section, and then the other processor will be entering in the critical section. So that time duration is called synchronization delay. So synchronization delay means after one processor has come out of the critical section, how much time that the algorithm is taking, before another processor or another site enters into the critical section. So that is our synchronization delay. So the last one, last performance metric is system throughput, which is equal to 1 upon SD plus E. That means at which speed the mutual exclusion algorithm is facilitating the processor's request to be satisfied. Okay, now we are going to see the algorithms one by one. So there are various types of mutual exclusion algorithms, that has been categorized into two categories, that is non-token based and the token based. So both in the both classification, token and the non-token, we have various types, many algorithms exist. Now in this chapter we are going to take two algorithm in non-token based category and two algorithm in token based category. So in non-token based category we are going to discuss Lamport algorithm and the Ricard-Agarwal algorithm, and in token based category we will be discussing about Suzuki-Kasami algorithm and Raymond tree based algorithms. So let us start with the first algorithm, which is non-token based algorithm, that is Lamport's algorithm. See, we had discussed about one algorithm in the previous chapter, that is for maintaining the logical clock in the distributed system, that is called Lamport's algorithm for logical clock, or Lamport's logical clock algorithm. Now this algorithm is also given by the Lamport. So herein this algorithm is nothing but Lamport's algorithm for mutual exclusion in distributed system, which was also given by the same person, that is Lamport. So this Lamport algorithm is a mutual exclusion algorithm which is non-token based algorithm. So that means there will be some set of rules that a processor will have to satisfy before the processor is allowed to use the critical section. So at any point in time only one processor will be satisfying the criteria that the Lamport algorithm has set. So now we are going to see how this algorithm works. Now for any site as I said is nothing but the processor. For any site Si, that means every site in the distributed system, they will be maintaining a queue that is called Ri, which is called request set. Now in this Ri, they will be storing all the requests for the critical section. So that means it can be their own request or it can be the request of other processor. So every site will be maintaining a request set wherein all the requests of the distributed system for a particular critical section will be stored in the timestamp manner. So that means the request that will be stored in the request set will have a timestamp at what time that request message was generated, and it will be stored in the request set of every processor in the order. That means based on their request timestamp. And it requires the algorithms to deliver the messages in the FIFO order. So that means what happens in the Lamport algorithm is, the first point is every site will be maintaining a request set. Okay, that is for SI it will be RI. So in RI it will be storing the request for the critical section, all the requests for the critical section in the sorted order. So that sorting will be based on the timestamp of the request message. So at what time a processor had sent the request for using the critical section. Now all the algorithm that we will be discussing in this chapter will have three parts. One is what will happen whenever, okay, what is to be done whenever a process is requesting for critical section. That is the first part. Second one is what will happen whenever a processor is, or what is the condition when the processor is allowed to execute the critical section. And the third is, okay, what will be the steps that needs to be executed while releasing the critical section by the processor. So in all the mutual exclusion algorithm that we are going to discuss in this chapter, we'll have this three part. The first is how to request for the critical section. Okay, the second part is when a processor will be allowed to enter the critical section, that is executing critical section. And the third part is when the processor has finished the execution of critical section, what are the things that the processor will have to do, okay, or other processor will also be doing, okay, while releasing the critical section. So similarly here also in the Lamport algorithm also we have three different phases. Now the first part of the algorithm is requesting the critical section. So if a processor wants to use the critical section, let us say a site SI wants to use the critical section, then it will have to send a request message, and that request message will have this format, that is TSI, I. So whenever a processor wants to, or the site wants to use critical section, it will have to send a request message to all other processor or all other site in the distributed system. Now there is a format for request message, and the format is TSI, I. So TSI means timestamp of site I. So at what time the message was generated. This is a logical time. I means ID of the site which is currently sending the request message. So whenever a site wants to use the critical section, it will have to send the request message to all other site. Now when other site, okay, if a site receives a request message, let us say SJ is currently receiving the request message, that is TSI, I from site SI, then it will do the entry in its request queue. Similarly in the SI site also, it will be entering the information about the request message in the request queue. So what happens is that, let us say we have site SI, okay, and it wants to enter in the critical section. So what it does is that, as I said, every site will be maintaining the request queue. So SI will be entering this information, that is TSI, I in the request queue, and then it will be sending the the same copy of the request message to all other site in the distributed system. Now any other site, if they receive the request message, what they will do is they will again create a entry in their request queue, okay, and then they will be putting that request message of site I in the request queue. Now if there are other request messages already there in the request queue, then this particular request will be placed in the sorted order, sorted based on the timestamp. Okay, so it will be in the order in which the request was generated by different sites of the distributed system. So this is what happens when a site requests for the critical section. Now next we are going to see the condition when a site will be allowed to enter in the critical section. So there are two conditions that has to be satisfied by a site to enter in the critical section, and these are the two conditions. So both has to be satisfied, then only a site will be allowed to enter the critical section. Now the first condition is a site will be allowed to enter the critical section if that site has received messages from other site with timestamp larger than its own request messages timestamp. So that means timestamp is denoting or defining which site had sent the request before. Okay, so if SI has received the messages from other site, okay, in such a way that in all the messages that it has received from the other side, the timestamp of the message is larger. That means those messages was generated after that site SI had sent the request message. That is the first criteria. Second is when the site SI's request, its own request is in the top of the request queue. As I said, every site will be maintaining the request queue, and every request that the site generates or receives from the other site will be, that request message will be entered in the request queue in the sorted order. So that means if a site SI's own request is in the top of the request queue, along with that, if SI has received messages from all other site, okay, with the timestamp larger than its own request message timestamp, then the site SI will be allowed to enter in the critical section. So this is the condition that has to be satisfied. Now the third part of the algorithm is, once the site finishes the execution of critical section, site will be releasing that critical section, and what are the things it will have to do while releasing the critical section. The first step is SI, when it is moving out of the critical section, it will have to send release message to all other site. Along with that, it will have to remove its own entry from the request queue, its own request queue. Now every other site, let us say SJ, after receiving the request message, release message, what they will do is they will be removing that particular entry from top of the request queue. So that request message will be on top in their request queue also, so that will be simply removed. So these are the things that has to be done. Now if we see the performance, there are many performance metric, but the first one we will be discussing here, that is number of messages per CS invocation. So for one time, to use the critical section for one time by any site, how many message communication it will have to do. Okay, let us say SI want to enter in the critical section, then what are the things SI is doing? So the first step is SI is sending a request message to all other site. Second is it will be waiting to receive the reply message from all other site. Okay, now after that, based on the condition, two conditions satisfied, okay, the site will be executing the critical section and it will be releasing the critical section. So after releasing the critical section, the site will have to send again the release message to all other site in the distributed system. So in total, okay, to use a critical section for one time, how many messages a site is how many message communication will have to take place. Okay, so that is the number of messages per CS invocation. Now how many messages will have to be communicated, let us calculate it. Now let us say there are n number of processor in the distributed system. Okay, now out of n, SI is one of them. Okay, so when SI want to enter in the critical section, it will be sending the request message to all other site. So in total, if there are n number of site and one of them is SI, that means SI is sending request message to remaining n-1 number of other sites. Similarly, n-1 other site will be sending reply message to SI. Now once SI releases the critical section, again it will be sending an release message to all remaining sites, that is remaining n minus 1 number of sites. So the total number of messages communication that takes place is n minus 1 request messages, n minus 1 reply message, and n minus 1 release message, and that gives us total of 3 into n minus 1 total messages per CS invocation. Okay. So this was one of the performance criteria. Second one is synchronization delay. Synchronization delay means after a site has released the critical section, okay, how much time that the algorithm requires, okay, before allowing another site to enter in the critical section. So it is like in the best case, if we have to see for the Lamport algorithm, so when a site will move out of the critical section, that site will be sending release message to all other site. Okay, let us say the time to send a message from one site to another site is T. Okay. So let us say T is the amount of time that on an average, this is the average time that a message takes to move from one site to another site in a distributed system. Okay. So we are going to calculate the synchronization delay for Lamport algorithm. That is, after a site, okay, leaves the critical section, it will be sending release message to all other site. Though it is sending to n minus 1 number of other site, but all messages are going parallelly, so it is, let us say on an average, it's the T amount of time, okay, to other site receive the release message. Now once the other side receives the release message, okay, they will be deleting the entry from top of the queue, and if one of their the other side's request is on top of the queue, then the other side will be entering in the critical section. Okay, so to enter in the critical section, again let us say it is taking, sorry, once the release message is reached to the other side will be deleting the top entry and the other side will be entering in the critical section. So that means synchronization delay here is 2. It is for the, sorry, synchronization delay here is T. So that means it is the released message that needs to reach to all other site. Then only the other site will be allowed to enter in the critical section. Okay, similarly, based on that, we can calculate the throughput also, which is 1 upon SD plus E, which is equal to 1 upon T plus E. So this was about the performance of Lamport algorithm. Now let us see the example how the Lamport algorithm works. So I am repeating again. If a site wants to enter in the critical section, it will have to send a message which will have this format, that is TSI, comma I for site SI. TSI means at what time the request message was generated, and I is the ID of site I. Now after sending the request message, the site I will have to put this entry in the request queue, and all other site after receiving the request message, they will also be creating the entry for the request message in their request queue, and then they will be sending the reply message. Now if a site has received the reply message or the release message, okay, or combination of two from other side in such a way that all the message that it is receiving, its timestamp is higher than its own request timestamp, as well as its own request is on the top of the request queue, then the site will be entering in the critical section. Okay, so once the site enters in the critical section, once the site finishes the execution of critical section, it will be sending release message to all other sites. So this is about the algorithm. Now let us see the example. Now in this one, let us say at time 1, so let us say this is the time 1. So at time 1, logical time 1, S2 wants to enter in the critical section. So S2 will be creating a request message, and its value will be 1, 2. 1 because at time 1 S2 generated the request message, and comma 2 means the ID of site 2. So 1, 2 is the request message that will be generated by S2, and it will be sent to all other sites. So in total there are 3 sites. So S2 will be sending the request message to S1 and S3. Okay. Similarly, in between, let us say S1 also decided to enter in the critical section. So S1 will also be creating a request message, and the format of the request message will be at what time S1 wanted to enter in the CS, that is at time 2, and ID of S1 which is 1. So 2, 1. So this 2, 1 message is the request message of S1 which will be sent to S2 and S3. Now let us say the 2 request message is sent in the distributed system, and other side has received these 2 request messages. Now what will other side do is they will be sending reply message. So reply message to the requesting side, as well as they will be making entry of the request message in the request queue. Now at this time at this time S1 received the request message from S2, so it is sending the reply message to S2. Along with that, it is creating entry in the request queue. So its own entry was 2, 1 for S1, but when it received 1, 2 from S2, so as per the ordering, 1, 2 will come before 2, 1. So it is in the sorted order. So you sort as per the first value of the request message. So that is the timestamp. Similarly, let us say at this time S2 received the request message from S1. So S2's own queue was 2, 1 before. Now 1, 2 before. Now it will have to make the entry of 2, 1 again. Similarly, S3, let us say at this time S3 has received the request from S2, so that is 1, 2. So it will do the entry of 1, 2 in the request queue. Okay, now at this time S3 is receiving the request message from S1. So that request message is nothing but 2, 1. So again it will append 2, 1 in the request queue. So this is the second communication. So first what happened was it sent the request message to all other side, and in the second part all other side they did the entry in the request queue and they send the reply message. Okay, so time can be any time. Now after that, okay, now we can see here which site is allowed to enter in the critical section, which site has got the permission to enter in the critical section is based on 2 criteria. That means its own request has to be in the top of the request queue. Along with that, it has to receive the messages, that is nothing but the reply message here, because no other site has already entered in the critical section, so there will not be any release message. So here we can see that at this time S1 has got the reply from both the site, okay, that is S2 as well as S3, but its own request is not in the top of request queue. So S1 is not entering in the critical section. Now let us see S2. Okay, but before that time only, we can see here S2 has received the reply from all other site. Okay, their replies timestamp will obviously be larger than its own request timestamp. Now at this time S2 has received the reply from all other side. Along with that, its own entry is also in the top of the request queue. So both the condition for that is required to enter in the critical section is getting satisfied at this point in time. So here S2 will be entering in the critical section. So S2 will be executing in the critical section for some duration, and after that S2 will be releasing the critical section. That means it will be sending release message to S1 as well as S3. So this is what is happening here in this slide. Now at this point in time, S2 got the permission as per the rule was satisfied. So S2 is executing, and then from the green line we can see at this time S2 is leaving the critical section and it is sending the release message to S1 and S3. Now what happened was, okay, till this time S1 was not entering in the critical section even though it received the reply from S2 along with S3, but the request of S2 was still on the top of the request queue. Now when S1 will be receiving the release message, S1 will be removing this top entry from the queue, okay, which is nothing but in the top entry it will be its own request message. So 2,1 will be there on top of the request queue. With that, it has also received the message from both S2 along with that S3, okay, whose timestamp is larger than 2. Okay, so this is the time when S1's criteria for entering into the critical section will be satisfied and S1 will be entering into the critical section. Now once S1 finishes the execution of CS, it will be sending the release message to S2 as well as S3, wherein they will also remove the top entry from the queue and ultimately their queue is vacant. So this is how Lamport algorithm works. So this is what is happening in this slide. Now next algorithm is Ricard-Agarwala algorithm, which is again non-token based algorithm. Now what was the limitation of Lamport algorithm? Lamport algorithm is again a very powerful algorithm in mutual exclusion field also, but there is a performance drawback, and that is number of message communication per CS invocation. In case of Lamport mutual exclusion algorithm, for any processor to use the critical section, it had to send 3 into n-1 number of messages, which is very large. Okay, when the value of n becomes very high, 3 into n-1 is a very large value. Now this has been reduced, okay, this has been optimized by another algorithm, which is Ricard-Agarwala algorithm. So wherein instead of 3 into n-1 number of messages which is required for CS invocation, for using the CS, Ricard-Agarwala algorithm use only 2 into n-1, or it requires only 2 into n-1 number of messages. Okay, so for one CS invocation, the number of messages Ricard-Agarwala algorithm requires is 2 into n-1. So this has been reduced. So algorithm is similar to that of Lamport mutual exclusion algorithm, but with a small refinement, because of which the number of messages per CS invocation has been reduced to 2 into n-1. So again, this algorithm is also divided into 3 phases. One is requesting critical section, executing, and the releasing critical section. So steps are also very similar. Here also, if SI want to enter in the critical section, okay, it will have to send the request message to all other site. Now any site SJ, if they receive the request message, okay, then they will be sending the reply message to SI, but before sending the reply message, they check these two condition. Okay, so that means other site SJ, they will not be sending reply message, okay, immediately, okay, if one criteria is if SJ is already sorry, let me just rub this first. Okay, so in the requesting critical section, what happens is that if a site SI want to enter in the critical section, as I said, it will be sending the request message to all other site. Along with that, it will be creating the entry in the request queue. Now the second step is when the other side receives the request message, okay, they will be sending the reply message only if this condition is satisfied. And the condition is, if that other side is neither requesting nor executing in the critical section, then they will be sending reply message immediately. Like in the previous example, it was S3 which was neither requesting nor executing the critical section. So S3 will be immediately sending the reply message. Okay. Or Sj is requesting for a critical section and with its own timestamp larger than that of the request message timestamp. So that means there can be two cases in the other side. Okay. When Si sends the request message, in Sj there can be two situations. One is Sj is neither requesting nor executing the critical section. That is the simplest one. Now the second one is if Sj also want to enter in the critical section, like for example S2 in case of previous example. Now in that case, before sending the reply message, Sj will check the timestamp. So if its own request message timestamp is larger than the timestamp of the request message which it is receiving from Si, then it will be sending the reply, otherwise reply will not be sent. Okay, so how Ricard Agarwala all in all it is working is, it is deferring the communication of reply message. So that means a site will not be sending a reply message, okay, if the site knows that that particular site should be entering in CS before that currently requesting site, then the reply message will not be sent. So reply message will be deferred. Okay, so reply will not be sent, okay, if Sj also wants to enter in the critical section and if Sj's own request timestamp is smaller than Si's request timestamp. So this is the steps in the requesting critical section phase. Now when a site will be allowed to enter in the critical section is when a site has received the reply message from all other site. Now once the execution of critical section is over, the site will be sending the reply message to all the deferred requests. So that means to whichever request the site had not sent the reply message, to all those sites, okay, it will be sending the reply messages. So all in all, if I have to summarize this algorithm, then what is happening is, in case of Lamport logical clock algorithm, 3 times communication was happening. That is when the request message was sent to all other site, when the reply message was sent by all other site, and at the end when release message was sent to all other site. In case of Ricard Agarwala, the request message will be sent to all other site, but reply message, okay, will be sent not by all the site. Okay, it will not be sent by those site who are also entering in the critical section, who also want to enter in the critical section, and their own request was before the currently requesting site's timestamp. Okay, so that means if the other site based on the timestamp knows that, okay, that other site should be entering in the CS before, then they will not be sending reply. Now that reply is called deferred reply. So they have to send the reply. Sj will have to send reply to Si, but they will not be sending reply immediately. So when they will be sending those deferred replies, when they finish their execution of CS. So once CS execution is over, they will be sending the reply message to all the deferred requests. So herein we need not be using the concept of release message at all. So what happens is that if a site has received reply message from all other site, then they will be entering in the critical section. So, and if in the distributed system, if there is at least one other site, okay, whose request timestamp is smaller than its own timestamp, that means it will not be receiving the reply message from that particular site, and hence it will have to wait until that other side do not finish the execution of critical section. So that is called deferred reply. So here we can see here the algorithm requires only two different set of messages. One is request message and the reply message. So in total n-1 request message and n-1 reply message, which makes it 2 into n-1 messages per CS invocation. The other performance metric, that is synchronization delay, if we have to calculate that, then after a site has lived or released the critical section, it will be sending the deferred reply, then only the other side will be entering in the critical section. So that means the time duration for reply to reach the next possible site to enter in the critical section is the synchronization delay, which is on an average we consider it as T. Okay, so T, as we had discussed previously, we will take capital T as the average time for a message to move from one site to another site in the distributed system. Now let us see the example, the same example as before. So at time 1, S2 want to enter in the critical section, so it will be sending 1,2 message to S1 as well as S3. Similarly at time 2, S1 want to enter in the CS, so it is sending 2,1 to S2 as well as S3. Now what happens if the other side receives the request message? Now at this time S3 is receiving the request message from S2. S3 is neither requesting nor executing in the critical section, so it will simply be sending the reply. Now at this time S3 is receiving request message from S1, which is again same thing. S3 is neither requesting nor executing in the critical section, so it will be sending the reply. But it is not the case in the other side. That means, let us see here, at this time S1 is receiving the request of S2, but S1 is also trying to enter in the critical section. Now it will have to check the second criteria, that is whether its own request timestamp is smaller than the timestamp of the request message. So its own request timestamp is 2 and the timestamp of request message is 1. So its own request timestamp is larger. So it will be sending the reply. Now at this time S2 is receiving the request message from S1. S2's own request timestamp is 1 and the timestamp in the request message which is coming from S1, it is 2. So 1 is smaller than 2. That means its own request timestamp is smaller than the timestamp in the request message which it is getting from the other side. At this time S2 will not be sending the reply to S1. So this particular reply is called deferred reply. Okay. Now when a site will be allowed to enter in critical section is when a site has received the reply from all other site. Now since S1's replies will be deferred by S2, S1 will not be receiving reply until S2 do not finish the execution. Now here we can see at this time S2 has received reply from both the other side, that is S1 as well as S3. So when it receives the reply from both the other side, it will be entering in the critical section. Now after executing the critical section, it will be sending reply message to only the deferred request. Okay, so to one of the other side, that is S1, S2 had not sent reply message, okay, during up till now. So once it finishes the execution of critical section, it will be sending that deferred reply to S1. Now this is the point when S1 has received reply from both the other side, that is S3 as well as S2. So this is the time when condition for entering into the critical section is satisfied. So S1 will be entering in the critical section. Okay, and once CS execution is over, as I said, deferred reply will be sent, but S1 had not saved any of the deferred reply, so just release the critical section. So this is how the algorithm, that is Ricard Agarwal algorithm, works. So this is the same thing, the same example that I discussed in the previous slide. So next is token based algorithms. Okay, so if we want to achieve mutual exclusion using token based algorithm, then the condition is the processor or the site will have to get the token. Okay, then only the site will be allowed to enter in the critical section. So all token based algorithm, there are so many, so all the algorithm, they have this basic criteria, that is the site will have to hold a token and then only the site will be allowed to enter in the critical section. So since there will be only one token for one CS at a time, only one site will be entering in the critical section. Now why there are so many types of token based algorithm is the different algorithm differs based on the way they search for the token. So if they want to enter in the critical section and how they are searching, which other processor is or the site is currently having the token, how they are getting the token, different algorithm differs in that. So out of various algorithm for the token based category, in this chapter we will be discussing about two token based algorithm, that is Suzuki Kasami algorithm and Raymond tree based algorithm. Now this token based algorithm, they use sequence number instead of timestamp. That means instead of logical time, all the token based algorithm, they use the sequence number. Sequence number is nothing but the number of their token request. So initially sequence number for every site will be 0. Now when they will be sending the request for the token for the first time, it will be incremented to 1. Okay, now later stage, if they want to request again, then sequence number will be incremented to 2 and so on. Okay, so sequence number represents the number or the or at what time, this is not the logical time, so at which number the site is currently requesting for the critical section or requesting for the token to enter in the critical section. So now we are going to see Suzuki Kasami algorithm. So in Suzuki Kasami algorithm, let us say we have a site SI. So every site SI will be maintaining a request set, that is Rn, for the site I. Okay, so its size will be n, that is nothing but the number of node in the distributed system. So every site SI will be maintaining the request set Rn, and there will be one token for one CS. Okay, and that token will have two information, that is one will be the Q, that is represented by ln. Okay, one is ln, one data structure. Another data structure will be a Q, a simple Q. So what you need to remember, what are the data structures that will be used in Suzuki Kasami algorithm is, one data structure is every site will be maintaining a request set RNI, and in the token there will be two data structure that will be maintained. One is ln, one is called last sequence number. I'll be defining about what is this and all, and the another data structure that will be maintained is Q. Now SI, it every site SI which will be maintaining a request set RNI, it will be storing the request message. Okay, now that request message will have this format, that is I comma SN. So I represents the ID of the requesting site, SN represents the sequence number. Okay, at in which number that particular site now currently is requesting for the token. Now when a site want to enter in the critical section, it will be sending this request which will have two information. This message will have two information, that is I and SN, to all other site. Along with that, it will also be doing entry in its own RN set, that is request set. Now other site also, if they are receiving the request message, let us say for site SJ, when it receives the request message from SI, okay, it will be entering that request message into its request set only if, okay, only after updating this value. Okay, the condition will be checked, and the condition is its own entry. Okay, that is in the request set, it will check whether for that site SI, whether it had already received a request message or not. So if it had already received a request message, then it will be checking the sequence number in that request message, and that sequence number will be compared with the sequence number which is present, which will be there in the current or in the new request message which it is receiving currently from SI. Okay, so what I am trying to say is that what happens is that in a distributed system, because n number of messages gets communicated via n different paths and all, there can be a situation when a site may be receiving the outdated request message again. Okay, there can be a situation when some request message is already received, it has been already entered in the request queue, or that request is already satisfied, that is token is already given, and after that it is receiving duplicate copy of same request message. This is because of the limitation of computer network. So how this is Suzuki Kasami deals with that is, since every site will be maintaining the request set, let us say this is the request set, so for any ith entry, if it receives a new request message, okay, then sequence number in that new request message or the current request message and the sequence number which is already there in the request queue, okay, will be compared, and that request message will be entered in the request queue. That means that sequence number will be updated, okay, provided if it is the larger value. So whichever one is larger, that means whichever request is the newest, okay, or the current one, the updated one, that will be entered in the queue. So if the request set already has the request message whose sequence number is larger than the sequence number which it is getting from in the current request message, then the entry will not be done. Okay, otherwise the sequence number will be updated in the request queue. Now again, this algorithm has been divided into three phases, similar to the previous algorithm that we discussed. The first part is what happens when a site wants to enter in the critical section, that is requesting critical section, executing critical section, and releasing the critical section. So when a site want to enter in the critical section, as I said, SI will be sending a request message with the sequence number, that is I, SN messages to all other site. Now every other site, they will be checking and updating their request set, okay, provided if it is the outdated or stale request message, then it will not be entered in the request set. Now if SJ has idle token, the token that SJ is not currently using, then it will be sending to SI with this, after checking this particular condition. Now what it says is that if that particular site has token already, then in that token Okay, there we are maintaining a data structure that is ln, that is last sequence number which is already served. Okay, so ln is going to hold the sequence number of all the sites, okay, which is satisfied. That means that particular request has been satisfied by giving the token. Now if the condition is, if the current request sequence number is equal to the last processed sequence number plus 1, that means the next sequence number for site I which needs to be satisfied, then the token will be sent back to send, or Sj will be giving that token to Si. Okay, so based on the condition, the token will be given to Si. Now executing critical section is very simple in case of token based algorithm, that when a site will be allowed to enter in CS if the site has received the token. Now after releasing the token, after releasing the critical section, what are the things that the site will have to do? Okay, so releasing the critical section means site will have to update the ln set. So ln will be, as I said, token will have two data structure, one is ln and q. In ln, it is going to contain the sequence number of all the site, okay, which is already served. So since the sequence number of site Si currently, let us say, has been served, then ln I has to be updated. Okay, now this queue will contain, okay, those sites ID, okay, which are currently requesting for CS, okay, that are in the waiting mode to receive the CS. And the top of the queue will contain that site which is the next eligible. Top of the queue is going to contain the ID of that site which is next eligible for the token. So while sending token from top of the queue, ID will be taken out, and to that ID token will be sent by the site which is currently coming out of the critical section. So this is what has been discussed. Design issues of the algorithm. So this Suzuki-Kasami has distinguished outdated request message from the current request message based on the sequence number. So when a site receives a request message, okay, before making entry of that request message in the request queue, it checks whether it has the updated request message from the requesting site or not. Okay, now how it is determining which site has outstanding request for critical section is by comparing Rn and Ln data structures. So Rn, which will be maintained by the site itself, Ln, which will be present in the queue, and that contains all the processed sequence number. So just compare it. If Rn value for the ith location is 1 greater than ln value of ith location, then the token will be sent. So this is the example how Suzuki-Kasami works. Okay, so as we can see here, let us say here we have 5 sites in our distributed system. So 5 site means every site will be maintaining the Rn set, okay, that is going to have the entry of the request message. Now let us say initially site 0 is currently using the critical section, that means it is currently having the token. So this is the initial condition of all the request set. So from this request set, what we can understand is that the first entry belongs to site 0. Okay, so 0th entry, let us say. So that means site 0's current request sequence number is 1. So site 0 had already sent the request message to all other site and they have already updated it, and its sequence number is 1. And in the queue, in the token, okay, as I said, token maintains the two data structure, that is ln and q. In the last data structure, that is ln data structure, okay, currently site 0 is executing in the critical section, and no sites sequence number has been satisfied till now. Okay, no site has completed the execution of critical section, so it is all 0. So ln set in the token is all 0, and q is also empty because next site to whom the token is to be sent, okay, that is also not there. Now this is the initial state, for example. Now let us see, after some time site 1 and 2 is sending request to enter in the critical section. So 1 and 2, their sequence number previously was 0, now for both of them it is 1 and 1. So that 1 1 will be sent to all other site and they will be doing entry. Okay, for the site 0 it was already 1. Okay, now since 1 also want to enter in the CS, so second entry is 1. 2 also want to enter in CS, so third entry is also 1. So this is how it will be for all the sites. Now let us say still site 0 is currently executing in the critical section only. Now let us say site 0 want to exit from the critical section. So when it will be exiting from the critical section, it will have to update the ln set, update the queue, take out the top entry from the queue and send token, okay, which has been identified based on the top entry in the queue. So queue is going to hold the ID of the remaining site which is currently requesting for critical section. Now this is the condition of Rn set for all the sites. So when site 0 want to exit the critical section, so first of all it will be updating the ln set of the queue. So sorry, ln set of the token. So in the token, these are the two data structure that is there. For site 0, its first request is served. Okay, it has been satisfied. So the first entry will in the token is 1. So remaining all 0. And 1 wanted to enter, so that 1 was there in the token, which will be removed. Okay, this will not be there. Sorry. 1 wants to enter in the critical section, that is this one want to enter in the critical section next. So from top of the queue 1 will be removed and this token will be sent to the site which is defined by the top of the queue, that is 1. So next site which will be getting the token will be 1. Similarly, okay, when 1 will be receiving the token, this is the condition in the data structure of the token. Okay, so 1 will be executing the critical section because it has received the token, and once it finishes the execution of the CS, okay, if no other site in between send the request, then on top of the queue it is 2 only, still 2 only. So this 2 will be removed and token will be sent back to the back to the site 2. But here what is happening is during that process 0 and 3 again is sending request to enter in the critical section. So for 0 now the sequence number is 2 because first request is already sent and already served. Now it is sending the second time request. So in the request message the sequence number will be 2. So 2 will be updated to all other site. Similarly for 3, for site 3 it is the first request message. So the entry for 3, that is the fourth position in which is the index in the set is starting from 0. So fourth position is 1 which will be updated in all other sites. Now here 1 was currently having the token site 1 and then let us say it has finished the execution of critical section. Now what it will have to do is it will have to update this ln set and take out the topmost entry and send the token to that entry. So how the entry in the queue is getting made is by comparing the Rn and ln set. So if we compare Rn and ln set, we will be getting the outstanding request, outstanding site, okay, which are currently requesting for the critical section. So if that particular sequence number is already processed, then that id will not go to queue. Now if that particular sequence number for that site is not yet processed, then id will go to the queue. So we need to compare Rn and ln. If Rn in ith location is greater than ln in ith location, then id will be copied to queue, otherwise it will not be copied. So when site 1 finishes the execution of critical section, okay, so it will be updating the ln set, that means which was previously 0, now it will become 1. Then site 1 will compare Rn and ln, okay. So 2 for the first entry, it is 2 and 1. So 2 and 1 means Rn at 0 location and ln at 0 location. If you compare, then Rn at 0 location is greater than ln at 0 location. So that entry will go to queue, that id will go to queue, that is id is 0, site 0. In the next location it is 1 and 0, okay, so sorry, the second location will be 1 and 1, so it is same, so it will not be copied. Third location is 1 and 0, so its corresponding id will be copied to the queue. Now fourth location again is 1 and 0, so that will be copied. So if it is not already copied, so 1 and 0, that is the fourth location for site 3, which will be copied and entered in the queue, okay. Now after that the topmost entry will be deleted. So this 2 was not entered here, 2 was entered before, okay, by the site 0 itself, so it was already there, so that is why it is in the top already. Now topmost entry, that is 2, that is site 2, will be getting the token next. So 1 will be sending the token with this 2 data structure to 2. So this is what is happening. So when 2 will be getting the token, this will be the condition of the token ln and q, okay. So just comparing, and this is how the Suzuki Kasami works. Now next algorithm is token based algorithm, is Raymond tree based algorithm. So how this algorithm works is, every site, again this is also a token based algorithm, so that means if a site want to enter in the critical section, it will have to get the token. Now herein each site will be maintaining a variable also, that is called holder variable, and that holder variable will be pointing to next site, which is towards the site which is currently holding the token. So what happens is that on this process, all the site will be logically arranged in form of tree. That is not the physical arrangement or the physical topology. That is not a physical tree topology, but it is a logical topology. So what I am trying to say is that every site, they will have a holder variable, and that is that will be giving the direction, okay. That is going to contain, that variable is going to contain the id of next site, which is towards the site which is currently having the token, okay. And that site which is currently having the token for this logical tree will be the root node. So logically all the site will be arranged in form of tree, and with that every site will be maintaining a request queue, okay. Request queue means it can be its own request will be entered or request of another site, similar to the previous example. So there are two data structure that will be used in Raymond tree based algorithm. One is every site will be maintaining a request queue wherein any request message, its own or other site's request message, will be entered, and every site will be maintaining a holder variable that is going to point, that is going to give direction towards the site currently having the token. Now, how this Raymond tree based algorithm works is, so whenever a site want to enter in the critical section, it will be sending a request message to the other site, okay, which is in the direction of the root node, because root will be the site which is currently holding the token. So after in the next step, if another site holds the token, then all the direction will be changed towards that other site. So these are the steps of Raymond tree based algorithm. So how it is going to work is, so the process is same, that if a site want to enter in CS, it will be sending the request message, okay. But to reduce the number of message communication, okay, to reduce the complexity, what Raymond tree based algorithm has done is, if a site has already sent a request message, it can be its own request message or the request message of another site, then it will not be sending another request message again, because ultimately only one request message will be satisfied. Now another request message will be stored by that site itself, and that will be satisfied later on, okay. So that is what happens is that in this algorithm, if a site want to enter in the critical section, okay, it will be creating a request message, and it will be sending that request message only if it has not previously sent any other request message. So if it has already sent another site's request message or its own previous request message, then which is not yet satisfied, then the new request message will not be forwarded to the next step. That will be stored in the request queue. That is the main purpose of request queue here. Similarly, let us say that site had not sent request message previously, then it will be sending that message to the other site. Now in the other site, if that other site has already sent the request message, then it will not be forwarding, it will simply put it into the request queue. So what happens is that in every step, okay, only one request will be forwarded by any site. Now ultimately, the site which is currently having the token will be getting the request message, and it may get the request message from multiple child, okay, in the logical tree. Now whichever request message was received first, that will be satisfied. That means towards that direction token will be sent, and if there is any other request message in its queue already, then to that request message will be sent following the token. Now we will try to understand this in detail with the example. Okay, we will see this performance after some time. Let us take this example. Let us consider this scenario. Okay, so here what is happening is, S1 is the site which is currently having the token. So how do we know about it? Is because all the direction, okay, if we see the direction, all the site has been logically arranged in form of tree like structure, wherein S1 is the root. Now all other site, that is S2, S3, S4, S5, S6 and S7, okay, their holder variable is pointing towards S1. So that means S4 will be, the holder variable of S4 will have ID of S2. Similarly S5, its holder variable will have ID of S2. Similarly S6, S7, their holder variable will have ID of S3. And S2's holder variable will have ID of S1. S3's holder variable will have ID of S1. So from the holder variable, site will get to know about in which direction the request is to be sent, okay, so as to get the token. Now as I said, every site will be maintaining the request queue. Okay. Now in the process, let us say if S6 want to enter in the critical section. Now it will check the request queue. If the request queue is empty, that means it has not already sent any other request to the next node. So it will create entry in the request queue. Okay. Then that request message will be sent to S3. Now S3 also checks its request queue. If it is empty, means no other request was sent previously. So that request will be forwarded to S1 and also the entry will be created here. Now similarly, at the same time, let us say S5 also wanted to enter in CS. So its request queue is also empty. So 5 will be entered here. Request of 5 will be entered and message will be sent to S2. S2's queue is also empty. So 5 will be entered here and the request message will be sent to S1. So S1 is getting two requests, 5 and 6, whichever was received earlier. Okay, that will be there in the request queue of S1. So 6 was received before 5. So 6 and 5 will be present in the request queue of S1. Now when S1 will finish the execution of CS, okay, the topmost entry will be removed and from whichever direction that entry had come, to that direction token will be sent. So that means to this direction token will be sent. Now after sending token, if S1's request queue is non-empty, that means if there was some another site also which also wanted to enter in CS, then that ID will be sent following the token. So token will be followed by another request, that is request of 5, site 5. So two things will go, okay, in return, that is token followed by request message of S5. Now when S3 will be receiving the token, top entry will be removed and towards that entry token will be sent. Now when S3 is receiving 5, that 5 request message of 5 will be entered in the queue and 5 will be sent to S6 because its request queue was empty. The first one was removed. Now when S6 will be receiving the token, okay, top entry will be removed and 5 will be entered in the queue, okay, and then since S6 has got the token, it will be executing in the critical section, and after coming out of the critical section, top entry again here will be removed and token will be sent towards that site from where this entry had come. So that means in the reverse direction to this direction, token will be sent to S3. So there is no other entry here, so only token will go from S6 to S3, then S3 to S1, then S2, and then finally S5 will get the token. So this is how the entire process is going to work. Now let us see the another situation. Let us say that S7 also wanted to enter. S7 wanted to enter in the CS. So S7 will be sending the request to S3. That S3 will be forwarding to S1. So S1 has got the request of 7. So which it will be entering in the queue. Okay. Let us see this scenario. Now after this, if S6 want to enter in CS, since its own entry request set is empty, so 6 will be entered and that 6 ID request message will be sent to S3. S3 will create entry here, but that request message will not be forwarded. Okay, request message of S6 will not be forwarded because it knows that it has already forwarded the request message of S7. Ultimately, after site 7 is served, then only 6 will be served. So S3 knows about it and S3 will be in between this communication. So this request of S6 will only be kept in the queue, but will not, its copy will not be forwarded to S1. Now what happens is that when S1 will finish the execution, then the token will be sent after removing the top entry from the set, that is 7 will be removed. 7 had come from S3, so to S3 token will be sent. So S3 will be getting the token, S3 will be taking out top entry from the queue, token will be sent to S7, but token will be followed by 6 because S3's queue is non-empty. So after forwarding token, if the queue is non-empty, then topmost entry will be sent along with the following the token. So topmost entry means 6, that is the ID of 6 will also be sent following token to S7. So S7 has got the token, so it will be entering in the queue in the critical section. Along with that, it is also receiving the request message of S6 which S3 had saved previously. So that means 6 will go into the request queue of S7. So when S7 will finish the execution of CS, then topmost entry, that is 6, will be removed, and then token will be sent to S3 because from S3 6 had come, and S3 will be forwarding that token to, S3 will be removing topmost entry and will be forwarding that token to S6. S6 after getting the token will remove the top entry from the queue, and then critical section execution will begin for S6. Now this is how Raymond tree based algorithm works, and why it is not forwarding the request of S6 to S1 is to reduce the number of message communication, because on the process S3 will be there in between, and if only S3 maintains this information, that much is sufficient, which is nothing but if a site has already forwarded the request of some another site, then instead of forwarding another request, just keep the site will be keeping with itself, okay, and when it will get the token and token to be forwarded to another site, that other request will be sent along with the token. So this way total number of messages communication has been reduced by Raymond tree based algorithm. Now let us see the performance. So what we have seen is that in the Raymond tree based algorithm, for how long a site's message is to be communicated or transmitted. So that means, let us see S6, okay, if it want token, then maximum number of times that the message will have to travel is from S6 to S3 and S3 to S1, okay, or on an average it has to go up to some intermediate label, because up to there only the request message will be there, and from after that it will go to the other side to whom the token is getting served next. So since this is entire structure is a tree structure, and we know the height of the tree is nothing but log n. N means total number of site. So on an average, if we have to see, then how many times message will be communicated is from S6 it will have to go to S3, that is one communication. From S3 it will go to S1, that is second message communication. Though message is same, but this is the second time communication of the message. So this way, so on an average if we have to see, then how many messages will be required, okay, for communication is for one CS invocation, the number of message communication will be from S6 will go to S3, then S1, okay, then let us say from S1 to S3, then S6. So it is your log n plus log n number of messages that will be communicated. So if we have to represent it in form of big O notation, then big O of log n number of message communication will be required. Similarly, what will be the synchronization delay, that is after a site has exited from the critical section and before another site enters into the critical section, how much time it is going to take, okay. So let us say when site S1 comes out of the critical section, it will be sending token to S6. Okay, so this is the maximum case wherein requesting site is in the last label. Okay, so token will be present in the root label, and if the requesting site is in the last label, then message will have to be communicated for log n number of times. So this is first time, second time, third time, and so on. Okay, let us say for one time communication, if it is taking t amount of time, okay, so from root to go to the leaf node, it is t into log n time, but it may not always be leaf node. It can, most of the time it can be the intermediate node. So if we take the average value, then it will be t into log n by 2. That will be the synchronization delay. Okay, so this is what it has been shown, and this is the same example that I was discussing. You all can just go through this example, and if there is any doubt, you can ask me. So this is about the mutual exclusion algorithm. So here we discuss about the 4 algorithm, that is Lamport mutual exclusion algorithm, Ricard-Agarwala, and these two were non-token based algorithm. And in the token based algorithm, we discuss about the Suzuki-Kasami algorithm and Raymond tree based algorithm. Okay.